In today's video, we're going to be talking about the first derivative test, which is a way we can figure out what a graph looks like using its first derivative. You may remember in past lessons, if we had a derivative, say f of x is equal to x squared, we could take the first derivative, which of course is just f prime of x, and that's equal to 2x by the power rule. Using this first derivative, we can actually find out some things about the graph without having to actually graph the function. So let's talk about that here. But before we go too much further, I want to talk about the monotone function theorem, also known as MFT. That sounds a lot like NFT, but unlike that, MFT is actually useful. If f prime of c is greater than 0, then the function f is increasing at that point. If f prime of c is less than 0, it's decreasing. And if it equals 0, then the function is not changing, aka the slope is constant. C is simply just the point on the graph that we chose for this function. So what this theorem tells us is that we can use the first derivative of a function to figure out where a graph is increasing and decreasing without having to draw the graph at all. Let's say we had something that looked like this. Say this is 0, this is 8, and this is -7. Let's say our graph looks something like this. This red line represents the first derivative of our function. Wherever the function dips below the x-axis, this function is decreasing, or negative. Wherever it is above the x-axis, this function is increasing, or positive. We can use this in order to determine where functions are increasing and decreasing. The points of interest, such as -7, 0, and 8, are our critical points, which I talked about in my last video. We'll talk more about that when we do an example problem, as it's a little easier to understand there. Let's do two example problems for this video. In our first example, we have the function x cubed minus 3x squared minus 9x plus 1. We have two things that we're trying to find. We need to find where f is increasing and decreasing, and we also need to find the extremums, aka the maximum and minimums of the function. Since this is a huge pain in the butt to graph, we should use the first derivative test to find all of this information. So what we're going to do is build a sign chart. Remember earlier when I was talking about 0, 8, and -7, and we figure out where it's increasing and decreasing? This is a sign chart. We're going to find something that looks very similar to this. Obviously, this isn't the one we're going to use, but we'll find that as we solve this problem. The first thing we need to do in this problem is find the derivative of f of x. That, of course, is f prime of x, and we're only looking for the first derivative here. We'll talk about the second derivative test in a future video, but let's do the first derivative test first. F prime of x is just equal to the derivative of f of x. Using the power rule, we get that the derivative of x cubed is 3x squared, the derivative of -3x squared is -6x, and the derivative of -9x is just -9. The derivative of 1 is just 0 because the derivative of any constant is just 0. Now we need to find the critical points using this derivative. To find those critical points, we just need to find where this equals 0. Because if it equals 0, then that is either a relative maximum or minimum because the function is changing from increasing to decreasing. So this function turns into 3 times x squared minus 2x minus 3 is equal to 0. And I gotta say, this function looks awfully factorable, and in fact it is. So we can change this function once again. We still have our 3 at the front, but since we have an x squared, we know that one of our factors has to be x and the other one also has to be x. And this of course still equals 0. Now we just need to find two factors that add up to be -2 and multiply to be -3. And those two factors are -3 and +1. X times x is x squared, x times 1 is x, -3 times x is -3x, x minus 3x is equal to -2x, and then -3 times 1 is -3. So this factor does work. Now that we have this, we know that each one of these individual factors must equal 0. We don't have to worry about the constant, but we do need to worry about these two, because if one of these two equals 0, then the whole function equals 0. 3 minus 3 will equal 0, and -1 plus 1 will equal 0. So x is equal to 3 and -1. And these are our critical points. And we'll need these when we build our sign chart, which we're going to do next. Let's build out that sign chart. Our sign chart will look something like this. I'm gonna mark -1 here, 3 will be way over here, and I'm gonna mark 0. I know that's not even, but for our purposes, it's fine. So at -1 and 3, we know that our function will equal 0. So we need to find points in order to figure out where x is increasing and where it's decreasing. So let's find points that are not -1 and not 3. For example, let's plug in f prime of 2. In other words, we're going to plug in 2 for every f prime of x. But since this is equal to f prime of x, we're going to use this because it's a little easier to understand. It'll make more sense in just a second here, but since these two are equal, we're going to use the more factored version. So f prime of 2 is equal to 3 times 2 minus 3 times 2 plus 1. Here we have a positive number, here we have a positive number, but here we have a negative number, which means this entire function is negative. Let's try f prime of 0. It's not one of our critical points, and I already marked it on the graph, so may as well try it. F prime of 0 is equal to -9. Now the reason I know it's equal to -9 is because since this function and this function are the same, if we were to plug in f prime of 0 into our original function, these two would cancel out and we just get -9. Of course, this is a negative value. Now let's plug in a number that's slightly higher than 3, say f prime of 4. This is equal to 3 times 4 minus 3 times 4 plus 1. And since all of these are positive, this part of the function will also be positive. Oh, and actually I made a mistake just a minute here. We're trying to plug in f of -2 here, so this would be -2 minus 3 and -2 plus 1. Since these two are both negative and this is positive, this part of the function is actually positive. Sorry, I made a little mistake there, but this actually does make a huge difference and also corrects what I thought was right. Anyway, sorry about that. Let's continue knowing that this is now positive, this is negative, and this is positive. So behind -1, the function is increasing. So we know it looks something like this. It's going upward whenever we go lower than -1. But whenever we reach f prime of 0, which is slightly higher than -1, the function is decreasing. So it goes below the x-axis as such, something like that. But then we also know when f prime reaches 4, it's positive again. So that means the function continues to increase after f prime of 3. So now that we know this, we know that this area here is increasing. We know that this area between -1 and 3 is always decreasing, and we know all the area behind -1 is increasing. I should probably make that a little clearer, so this will be positive, negative, and positive. It's a little hard to see with the red on red. So what this graph tells us is that we know where f is increasing and decreasing. Remember, by the first derivative test, wherever f prime of x is less than 0, f is decreasing, and whenever f prime of x is greater than 0, f is increasing. So for part A, f is increasing. I'm going to write INC for increasing at, and we're going to use interval notation to mark where it's increasing. We know that anything below -1, it's increasing. So from -infinity all the way to -1, the function is increasing. And this function is still increasing at -1 and begins to decrease after -1. So we can include -1 here by denoting that with a bracket. Then f continues increasing after x equals 3. So we're going to put a little u here. This u stands for union. At 3, the function is still decreasing, so we can't include it. But from 3 to infinity, the function is increasing. Now, where's the function decreasing? Let's write that over here. And decreasing, which will be denoted with DEC dot. And the only place where this function is decreasing is between -1 and 3, as denoted on our sine graph. So it's decreasing between -1 and 3. So that's all of part A. Now we need to find the relative maximum and minimum. So what are our relative maximums and minimums? Well, -1 is a relative maximum, and 3 is a relative minimum. But why is it a relative maximum at -1? Well, remember, our function is increasing all the way up until -1. At -1, the function starts to decrease. And whenever the function is increasing and then starts to decrease, we have a relative maximum. And then at x equals 3, the function's been decreasing up until it reaches -3. Therefore, it dips like this, goes from decreasing to increasing. And when it does that, the function is a relative minimum. Think of the bottom of the parabola and the top of a parabola. So here's our answer. F is increasing at -infinity to -1 union 3 to infinity, and decreasing at -1 to 3. By the way, this is a parenthesis, not a bracket. And the relative maximum is at -1, and the relative minimum is at x equals 3. Let's do one more example for this video. In this example, we have the function f of x is equal to x squared plus 8x minus 3. And we want to find the same things as last time. We want to figure out where the function is increasing and decreasing, and we want to find the maximums and minimums of this function. Once again, if we find the first derivative, we can figure out all this information. So let's find out the first derivative of x squared plus 8x minus 3. This is denoted as f prime of x, and the derivative of x squared is equal to 2x using the power rule. The derivative of 8x is equal to just 8, and the derivative of any constant is just 0, so we don't even need to write it. So this is our derivative, and we can use this to find all of our information. Once again, we need to find critical points and figure out where this function equals 0. So in order to do that, we can subtract 8 from both sides. This turns into 2x is equal to -8, and if we divide both sides by 2, we get that x equals -4. And this is our only critical point in this problem, unlike last time where we had 2. So our sign chart is actually super easy to draw. Since we only have one critical point, we just have to put -4 here. And also, since we only have one critical point, we only need to test one number on the negative side and one number on the positive side of -4. So let's do that. First, let's plug in f prime of -5 and figure out if it's increasing or decreasing. This is equal to 2 times -5 plus 8, which is equal to -2, and obviously that's negative. Now we just need to plug in one number that's greater than -4. For this example, we'll use f prime of -3. It's just slightly above it, just like how -5 is slightly below it. This is equal to 2 times -3 plus 8, which is equal to +2, which is positive. So on the left-hand side of -4, or on the negative side, this function is decreasing, but on the right side, or the positive side, this function is increasing. So our sign chart is simply going to look like this. A little easier to draw because we just have to draw a line like that. So on this side, the function is decreasing or is negative, and on the right side, the other side, this function is positive or increasing. So using this sign chart and the data we found, we can figure out the absolute maximum and minimums of this function, along with where it's increasing and decreasing. First of all, at -4, since our function is equal to 0, this function is neither increasing or decreasing, so it cannot be put into our interval. In other words, we're just going to be using parentheses and not brackets. To answer part A, f is increasing, denoted as I and C because I'm lazy and don't want to write increasing, at negative infinity, oh, that's an 8, negative infinity up till 4. But we cannot include 4 because at 4, this function is equal to 0, which is neither increasing or decreasing. And this function, f, is decreasing at -4, I meant to write that there, to infinity. Once again, we can't use brackets because we cannot include -4, and we also cannot include infinity with brackets since infinity isn't really a number, it's just a concept. So this is part A answered. For B, what are the relative maximums and minimums? So we know that -4 is a minimum for f. There is no maximum on this function. The critical points, aka the only one that we have, is either a minimum or a maximum. And since we only have one critical point and it's a minimum, we don't even have a maximum in this problem in the first place. So this is our answer. And to be safe, I would write relative minimum, but since we do know this is a parabola, you could write absolute minimum and probably get away with it. I hope you enjoyed this video. I hope it was helpful, and I hope you learned something today. If you'd like more Calculus 1 lessons, be sure to check out the playlist linked here, and consider subscribing. I'm uploading all of Calculus 1 to this channel along with Cal 2, 3, and other lessons to come in the future. I'll see you guys in the next video.